In this lecture, we are going to talk about symmetry. So, symmetry plays an important role in particle physics. We will learn why that is the case because they are connected to conservation laws. So, if there are conservation law, there is a symmetry behind it, and if there is a symmetry, there is a conservation law behind it. We will dig deeper into this, what that mean. But let's just try to understand, get an idea what symmetries are and how can we use those symmetries. So, this is a very famous function. Imagine we have no idea what the functional form of this function is, but so how can we just from looking at the graph what information we can get from this function? One of the thing you can understand here is that it's the odd function. So the other thing you can look at, if you calculate value, for example here, and it's supposed to be like this. Here they're gonna be same, like f of x is equal to f of, it's gonna be negative, but let's just say square of this, both of them is gonna be equal. The other thing you can see here, since it's an odd function, if I calculate the integration here and here, that is gonna be 0. Calculating integration from negative pi to plus pi of this function, whatever this function is going to be 0. They're gonna cancel out. These kind of information you can just get from the symmetrical aspect of this graph. So these kind of things help you to understand more about your system without even doing anything. Okay, so now how does this help in physics? In physics, you might have heard of symmetry in crystals, but that's not what we're gonna talk about in this case. Okay, so one of the thing what Newton figured out that, so Newton figured out that the fundamental symmetries are not revealed in the motion, revealed in motion, but rather in the equations of motion. Okay, what that mean is that we know that the gravitation, we know that the gravitational laws of equation of motion are spherically symmetric, but the planet doesn't move in circles. Okay, we have elliptical orbit, so the equations, the symmetries are not revealed in the motion but rather in the equations of motion. So it's hard to understand what symmetries are hidden in the system from the solution. Okay, so how does one figure out? And this is where aminoids comes in, and this is one of the really important things in particle physics, this ME. And you have this Noether theorem, which says that where the symmetry mean there is some conservation law in your system. The symmetries are not revealed in the motions of the object, but they are revealed in the equation of motion. But if you're just looking at the system, what are the other ways you can find symmetries? And one way is that conservation laws. If you find some conservation laws, that means there is some symmetry in the system. Okay, so Amy Noether figured that out. What that mean is, if you have a translation, for example, if you have a translation in time, which mean the energy is conserved. Translation in space, which mean momentum is conserved. Or vice versa, if momentum is conserved, then you have a symmetry translation in space. Then you have rotation, which mean your angular momentum is conserved. And then you have the internal symmetry. We will talk about the gauge transformations. These point to conservation of charge. These point us to conservation of charge. So we have all these symmetries that if you have a symmetry in the system, you have a conservation law. If you have a conservation law, there is symmetry. So the lesson in this chapter is that the symmetries are not revealed in the motions of the object, but rather the equation of motions. You can understand what symmetries are there, but if you're just looking at the system, other ways to find symmetry, they look for conservation law. If there is a conservation law, there is symmetry. If you find a symmetry, there is a conservation law. So I hope you like this video. If you do, give the thumbs up, and I will see you next time.